Last episode, we discovered how a CFD solver represents the physical world using numbers. Today, we begin building the first real component of our solver. Every CFD solver begins by dividing the domain into small computational cells. Each of these cells will eventually store information about the flow. Later in this series, we'll use neighboring cells to solve the governing equations. By the end of this episode, you'll generate the same computational grid used by professional CFD solvers. And remember, the complete Python source code for this episode is already available through the links in the description, so you can focus on understanding the concepts while following along. Let's begin with something familiar. A pipe carrying fluid. Every part of this fluid is moving. Suppose we measure the velocity at one tiny location. At this point, the fluid has one specific velocity. Move somewhere else, and the velocity changes. In fact, every tiny location inside the pipe has its own value. Zoom in further, and you find even more locations. A real fluid contains essentially an infinite number of points. So how can a computer possibly solve a problem with infinitely many locations? The answer is surprisingly simple. Instead of remembering every point, we divide the domain into a finite number of small regions. These regions are called computational cells. Together, these cells form what we call the computational grid. Rather than solving the entire pipe at once, the solver treats each cell as one small problem. Later, each cell will store the flow variables at its center. Instead of remembering infinitely many values, the computer stores only one representative value for each cell. Repeat this process for every cell, and the entire flow becomes a collection of numbers that the computer can understand. This simple transformation is what makes computational fluid dynamics possible. Earlier, we divided our physical domain into computational cells. Each rectangle now represents one computational cell. Let's zoom in conceptually and study just one cell. Every computational cell has a center. The solver stores one representative value here. Information enters and leaves through the cell faces. Mass, momentum, and energy cross these faces. Every cell also communicates with its neighboring cells. These four ideas are the foundation of every finite volume solver. A real CFD simulation contains thousands, or even millions, of computational cells. Suppose we are solving this particular cell. We call it the present cell, or simply P. Its neighbor on the left is called the west cell. Its neighbor on the right is called the east cell. During every calculation, information moves between neighboring cells. Instead of writing long descriptions, we simply use symbols like U sub P, U sub W, and U sub E. This simple notation will appear throughout the rest of our CFD solver. So far, every computational cell has looked identical. Each cell stores its variables at the cell center. The distance between neighboring cell centers is called delta x. Notice that every neighboring pair has exactly the same spacing. When every cell has the same size, we call it a uniform grid. If the spacing changes from one cell to another, the grid becomes non-uniform. To keep things simple, we'll build our first CFD solver using a uniform grid. Our computational grid is now complete. But the computer still has one important question. How does it know where every cell is located? The answer is simple. Every cell center is assigned a coordinate. Together, these coordinates define the computational grid. Our computational grid is now complete. Each cell has a center where the solver stores information. For example, the velocity can be stored at every cell center. Pressure is stored there as well. The same idea applies to temperature and many other variables. Each computational cell becomes a small container holding all the information about the fluid at that location. During the simulation, neighboring cells continuously exchange information. The only thing missing now is the mathematical algorithm that updates these values. In the next episode, we'll write the first finite volume equation and finally begin building the CFD solver. Every cell has a well-defined center where the solver will store variables such as velocity, pressure, and temperature. So far, everything exists only as a diagram. But a real CFD solver needs numerical data, not pictures. The computer must know where every cell is located and allocate memory for the variables stored at each cell center. Let's translate this computational grid into Python, one step at a time. The first step is to define the physical domain. Here, we'll use a 1 meter long domain. We store this length in the variable L. Next, we choose 8 computational cells. Since every cell has the same width, the cell size is simply the domain length divided by the number of cells. Now our solver knows the size of every computational cell. Our domain is now divided into 8 computational cells. Instead of storing variables on the cell boundaries, the finite volume method stores them at the center of each control volume. NumPy can generate all of these cell center coordinates with a single line of code. These numbers represent the physical locations of every computational cell center. This single command automatically builds the coordinate system for our one-dimensional computational grid. Our computational grid is now ready. The next step is to store the physical variables that describe the fluid. For example, we may store the fluid velocity at the center of every computational cell. Similarly, pressure can also be stored at each cell center. Depending on the problem, we may also store temperature or other physical quantities. In Python, these variables are stored as arrays. Each element of the array corresponds to one computational cell. In other words, one array value stores the solution for exactly one computational cell. Our computational grid is ready, but the solver still doesn't know anything about the physical problem. Let's begin by specifying the temperature at the left boundary. Similarly, we prescribe the temperature at the right boundary. The temperatures inside the domain are still unknown. These are the values our CFD solver must calculate. In Python, we simply assign the known temperatures to the first and last cells of the computational domain. Only the boundary temperatures are known. Every interior value must be computed from the governing equations. The boundary temperatures are known, but every interior temperature remains unknown. Let's focus on one computational cell. If we can determine the temperature here, we can repeat the same procedure for every other cell. To compute the unknown temperatures, we begin with the governing equation for one-dimensional steady heat conduction. This equation expresses the conservation of energy. Our task is to convert it into a form that the computer can solve. Instead of solving the governing equation everywhere at once, the finite volume method solves it one control volume at a time. Let's isolate one control volume. We'll call the neighboring cells west and east, while the current cell is labeled P. Our governing equation is still written in differential form. Instead of applying it at a single point, we integrate it over the entire control volume. This simple step transforms the differential equation into its integral form, which is the foundation of the finite volume method. Congratulations! We've successfully built and executed the first component of our CFD solver. Starting from an empty Python file, we've built a computational grid that will serve as the foundation for every solver we develop in this series. In the next episode, we'll use this computational grid to solve our first fluid mechanics problem and take another major step toward building a complete CFD solver.